Hello everyone, welcome to our virtual talk today. My name is Ismail from the University of California, Riverside, and I'm going to talk about SPECCFI, a new mitigation for Spectre attacks using CFI-informed speculation. Recently, many attacks have emerged that target different components of the very complex processor microarchitecture. For example, Spectre class attacks exploit the predictor units, and meltdown type attacks exploit speculative execution after a fault happens in the system, and try to leak information from internal buffers like L1 data cache in original Meltdown attack, a store buffer and load ports in MDS attack, or field buffer in the zombie load attack. More recently, the load value injection attack showed that an attacker is able to inject a load value from different internal buffers into the transient execution of the victim process. As all of these vulnerabilities are rooted in the hardware, they are very hard to mitigate at software level, if not impossible. It's also important to note that we cannot defend against all of these attacks with a single solution. In this work, our focus is on the Spectre class of attack that exploits the predictor units in the processor. Let's go over the general overview of a Spectre attack. The victim and attacker process have to share a predictor unit. In most variants of Spectre, the attacker tries to redirect the transient execution of the victim process to access some sensitive data. Because of misprediction, the processor later will flush all the speculative instructions, but it may have already left secret-dependent traces in the CPU's microarchitectural state. Then the attacker needs a time-based side channel analysis like prime and probe or flush and reload to recover the secret data that has been loaded into the cache in the previous stage. There have been some attempts to stop Spectre attacks by preventing transient execution around branches. This has been done by having the compiler insert memory fences into the pipeline. However, they have to be conservative and insert these fences almost everywhere. That basically kills the performance benefit that we can get from speculative execution completely. And even so, they are only specific to a Spectre variant 1. The other class of solutions try to prevent the predictor poisoning by flushing the predictor on domain changes. This solution also keeps the attack vector within the same thread open, and experiments show that they too impose a high performance overhead. Another class of defenses try to close side channel attacks. However, there are numerous different channels in the CPU, and each one of these solutions can only close one of the many channels. For example, InvisiSpec and SafeSpec can only stop the leakage from cache-based side channel attacks, but not the port contention-based one. Also, they usually impose high performance overhead and need significant hardware modification. Um, by introducing SPECCFI, we offer a new solution for Spectre variant 2 and variant 5 that imposes very minimal performance overhead by just minor modification to the hardware. And before I show you how we protect against Spectre attack, I want to explain Spectre variant 2 in more details. Whenever a program executes an indirect branch, a hash of the branch address and the branch history will be indexed to the branch target buffer or BTB. And the processor will get the target address of this indirect branch from the BTB and starts fetching and executing a new stream of instructions speculatively. This transient execution is like traversing an edge on the control flow graph of the program. Now imagine that the attacker wants to inject the address of a malicious gadget at the address of the vulnerable branch in the victim's address space. To do so, he will execute an indirect jump from the same branch location to the address of the gadget in his address space. He would then be able to inject into the shared BTB. When the victim starts to execute the branch in location 0x20, the control flow of the victims will be redirected to the malicious gadget, which usually brings some secret data to the data cache. Then the attacker can do some analysis to recover the secret data using side channel techniques. Okay, our approach relies on CFI as I mentioned, and I want to kind of draw a parallel to control flow hijacking attacks here. If you remember control flow attacks, they exploit the memory corruption bugs through code pointer modifications technique. As a result of the attack, the control flow of the attackers will be redirected to a malicious gadget. The state-of-the-art solution for this kind of attacks is applying control flow integrity or CFI. If we try to see how it corresponds to a Spectre, we see that here the attacker also tries to exploit the fact that the branch predictor is shared between him and the victim by injecting his desired target to the BTB. The only difference here is that in this type of attack, attacker tries to hijack the speculative control flow. So the basic idea behind SPECCFI is to apply the principle of control flow integrity to a speculative execution of the program. So what does it mean to apply control flow integrity to a speculative execution? Basically, it falls down to making sure that even the speculative execution will follow the control flow graph of the program using CFI information. So let's look at this in more details. There is a static part to this idea, which does the control flow analysis of the program, and it's identical to existing hardware-based CFI. Now at runtime, we do two things. First, control flow integrity check or move earlier to the decode stage of the pipeline, and therefore we prevent illegal control flow during speculation. But this does not protect returns. So for backward edge, we extend the RSP to do validation also during the return speculative execution. The ISA modification is very similar to other hardware-based CFIs, and we do not need any new modifications to ISA to be able to apply CFI during speculation. So basically, we need to include the CFI label into the indirect call and jump instruction. Also, we need a new instruction to mark the valid target for each indirect branch. I should also mention that Intel and ARM already have a very similar extension for regular hardware CFI. The CFG computation is also similar to other CFI approaches. Basically, the compiler computes the valid target set for each indirect branch and assign a unique label to each set. So the indirect branch only can jump to the addresses in a set with a similar label. I should also mention that SPECCFI can utilize any kind of label-based CFI implementation, and both LLVM and GCC also support some kind of label-based CFI. Now let's see what needs to be happening in the decode stage. Starting from the initial state, if the CPU sees an instruction rather than indirect call or jump, it will stay in the same state. If an indirect branch has been decoded, then it will go to the next state, and using the BTB, it will fetch the next instruction window from the target address. Note that since the CPU eventually has to fetch from the target, fetching the CFI instruction will not affect the performance at all. We continue from this state, so if the first decoded instruction from the target is anything rather than the CFI label, an elfence instruction will be inserted to the pipeline. But if the first decoded instruction after the indirect branch is a CFI label, then we need to make sure that the label matches that of the branch. If it is a mismatch, again an elfence will be inserted to the pipeline. But if it is a match, it goes back to the initial space. As the SPECCFI tries to prevent both a speculative and regular control flow hijacking attack, a similar check will be done in a commit stage. Here is a very simple example to show a SPECCFI in action. Starting from the first basic block, the indirect branch will use the BTB and fetches from address A. The first instruction in A is a CFI label instruction with a matching label. So the speculative execution will continue without hurting the performance. Then the execution reaches the branch location at address 0x20. Based on the CFG, the basic block B and C are both legal targets for this branch. But according to the current status of the BTB, the CPU should fetch and execute from target B. Now assume that an attacker injects a new entry to the BTB at branch location 0x20 and tries to redirect the control flow to its desired address. The CPU will start fetching from the new address, but because the first decoded instruction is not a CFI label instruction, SPECCFI will stop the attack by inserting a fence into the pipeline. The backward edge defense component of SPECCFI protects mis-speculation on return instruction. Return instructions typically get their predicted addresses from a hardware stack called the return stack buffer or RSB, and this RSB is vulnerable to a range of Spectre attacks. Aside from that, to prevent normal backward edge attack, hardware CFI proposals use a shadow call stack or SCS, which is protected from normal memory reads and writes. Similar to the RSB, the SCS is used to keep the return address of the previously executed calls. With SPECCFI, we aim to defend against both Spectre RSB and also normal backward control flow attack. What is done is that we combine the traditional RSB and SCS into a unified structure, acting as both of them. Conceptually, RSB in our design can be viewed as an in-processor cache for the in-memory SCS. Note that this is different from other SCS implementations that retain the RSB separately. In case of context switch, we flush the speculative entries and keep the committed ones to use them after we get back to the same context. There are many more details about this design in the paper. To implement SPECCFI, we used LLVM to insert CFI check in our benchmark. Also, we implement the runtime check in the Mars x86 simulator, which is a full system cycle accurate simulator on top of the QEMU. We then evaluated the performance overhead of our design and compare it with other existing solutions using the SPEC17 benchmark, that is a C++ benchmark. However, 8 of 23 benchmarks are written in Fortran, and we couldn't compile them using LLVM. We evaluated the effectiveness of SPECCFI against real-world exploits. The result shows that SPECCFI can prevent all different vectors of Spectre VTB. Also, SPECCFI can mitigate all vectors of Spectre RSB and smarter Spectre attack. It's good to mention here that by combining our solution with an existing hardware-software solution for Spectre V1, we can close all variants of Spectre attack. Also, note that to complete the defense against Spectre V1, starting Spectre variant 2 and 5 is necessary because the V1 defense could easily be bypassed by using these two classes of attacks. We compare SPECCFI performance against 3 design points. As a baseline design, we use an unmodified, unprotected machine. The second design is Redpoline style software fencing, which adds fences to the indirect branches using compiler. So in this design, we change the compiler to do the following. Any indirect call and jump are replaced with a load, elfence, and call for protecting the forward edge. With the same approach for securing backward edge, we replace any return instruction with a sequence of pop, elfence, and jump instruction. The last approach here is all-target fencing that we show one implementation with an elfence inserted in the hardware at the target of each indirect branch and return. As you can see, inserting serializing instruction like elfence in the target of every indirect branch is expensive, causing a performance overhead of 39% and 48% on average for all target fencing and Redpoline style. Using SPECCFI, we only insert elephants when the CFI check fails. This causes the number of inserted elephants to drop significantly and reduces the performance overhead to less than only 1.9% on average. We studied the number of elephants inserted by different defenses. We can see that the number of elephants inserted by SPECCFI is much less than the others. That is in line with our performance result. Measuring the impact of forward and backward edges defense separately can also be insightful here, since they use separate mechanisms for protection. As for SPECCFI, the overhead cost from forward edge defense is typically very low because SPECCFI only insert fences on misspeculation. We also know that the prediction rate of the indirect branches is pretty high in the modern processors. So as a result, the number of inserted fences would be very low and performance overhead of forward edge defenses is close to zero. The major part of the SPECCFI overhead is due to backward edge defense, which is associated with both speculative and non-speculative defense. Our experiment shows that only a small portion of this overhead corresponds to Spectre attacks. So in this talk, we introduce SPECCFI, a CFI-based defense against Spectre attacks with low overhead and minor modification to the hardware. Thanks for your attention, and I would be happy to answer any question you might have.